people go on the bridge, how often that occurs. We have to define comfort evaluation for people, and we do that through literature review based on comfort and acceleration. And together with the clients, we define a performance objective for the structure, and we try to link the traffic and the comfort. So on the traffic classes, this is maybe what a bridge looks like 99% of the time. There's barely no one on there. From time to time, you might get a bit more people on it, and very rarely you have this kind of event where the bridge is fully packed. So with that, we define, actually we found in the literature 5 traffic classes, from very weak traffic to exceptionally dense traffic. And we found 3 different classes of comfort, and actually the very weak and weak traffic maybe occurs 95% of the time. So we decided that people should have the maximum comfort for this case. And for rarer events, we choose to have medium or low comfort on the structure. So other assumptions, because damping is actually hysteretic and not viscous in real structures, it depends on the amplitude of the oscillations. And if for seismic we design steel bridges with 2% damping, for comfort you have actually to take a very lower damping ratio, and you go down to 0.5%. And finally, we had to find what are the critical frequency of human walk, and we found in the literature that it's between 1.2 and 2.3 hertz for vertical modes, and because for horizontal modes, normal people actually alternate left and right foot, you get divide by 2. So with that, we went through a model analysis of the structure with the idea of having 90% of the effective mass that would be calculated. So we needed 40 modes for that. But actually, for the critical frequency that we showed you, we only have a few modes. The first one are actually rocking of the pylon, so they are not relevant for the cross-structure interaction and won't actually have any significant impact on the design for comfort. The third mode is interesting because here you get an horizontal mode that is within the range of critical frequency. It's fully horizontal, and we will have to take care of this one. Just a remark here, we have already with the 3 first mode 70% of the mass for effective mass, and for horizontal, hence the frequency are still very low, so we think that for earthquake design we won't have any problem with this bridge. And we had finally 3 vertical modes that are in the critical range of frequencies, so you see this kind of global modes of the decks, and so we had to take care of that more carefully with a footfall analysis. So within the footfall analysis, you specify a number of pedestrians, and you input the nodes that you want to excite, so the deck obviously, and you will get an acceleration, and you will get the maximum value for acceleration and displacement. And actually it turns out that the vertical modes are okay for design criterion, but that the first horizontal mode is a problem. So we had to do something for that. And our first idea was to maybe stiffen the structure, but the mode frequency is so low that we would have needed to have a very chunky structure that was not compatible with our architectural idea. So we had to find a passive damping solution, and more specifically a TMD, so or tube mass damper. So the idea is that if you have a single degree of freedom system, you can excite it to its resonant frequency, and you will get a huge response. But if you had another system that are the same frequency, when you will move this system, you will actually also excite this one, and this system will pump the kinetic energy out of this. And if you add a damper between these 2 elements, you will actually dissipate this kinetic energy that you pump from this system. So it's quite an efficient system. This is how it looks in real life. It's quite boring, but this is how it is. And here are the horizontal mode when we add the TMD. So now, because we add 1 degree of freedom, we get 2 modes and not 1 mode. So in the first one, the TMD is in phase with the structure. And as you see, the displacement of the TMD are way bigger than the displacement of the bridge. It's magnified, of course. And the second mode is actually the TMD going out of phase with the structure. So it proved that we succeeded in tuning the TMD to the frequency of the structure. And here, if you see the response of the structure for acceleration, the green curve is actually our initial design, and it was not good for acceleration. But we divided the amplitude of the acceleration by a factor of 2 or 3 by adding 2 times 450 TMD on the structure, which represents approximately 1% of the mass of the structure. And I know this kind of design is quite new, and so we went back to different examples that exist, and this is a bridge in Paris, which is also very standard. It's been designed with TMDs, and I'm pretty sure no one on the bridge knows that there are actually TMDs on it, and people are pretty confident in the design. And actually, one day I was on this bridge, and I took this picture, and I think this guy is really, really confident in the design. If I had the capacity to do that, I would do it on the bridge we want to deliver you. Unfortunately, I'm not. So I will just tell you that I'm really confident in our dynamic design, and I will hand to Dana for the connection details.
Alright, from there, we collected all the data required from the analysis team and we did some detailed design. So one of our major detailed design is a gusset plate located at the top of the panel, and it's located at every panel, so total 4 in total. So what you see over here is that the gusset plate will be carrying a total of 15 cables, 11 spanning over the main span, and 4 backspan cables connected to the hydraulic jet. And in between we'll have a cable spanning between the 2 panels to allow natural stability. And this is going to be fixed to the panel. With respect to the shape of our gusset plate, we decided to have all the cables and the cable sockets exposed versus having it hidden. And the reason for that is to allow the user to understand the structural system of the bridge, because it all comes down to the details to have a better understanding of how the bridge works. But what mainly governed our design configuration for this gusset plate were the size of the cable sockets. Since we have a lot of cables spanning along the bridge of varying dimensions, the cable sockets with varying dimensions, they're quite big in size. But with respect to our design strategy, initially we pick a plate thickness, and from there we calculate the plate capacity. And then we check and see if the forces are sufficient to carry the forces applied on the gusset plate. If not, we'll go back and change the thickness of the plate and repeat this process until we get a plate thickness that satisfies all the design requirements. But what majorly governed our design are the out-of-plane forces acting on the gusset plate. And the reason for that is once we open the bridge, the backspan cables are no longer in plane with the rest of the bridge, hence causing out-of-plane forces to act on the gusset plate. But we were able to minimize these forces by having the bridge skewed to the shore instead of having it perpendicular to the shore. So by skewing the bridge, we decreased the angle of rotation required to meet a clearance of 25 feet to allow for boat trafficking, and therefore decrease the forces acting on the gusset plate. We came up with a thickness of 2.5 inches that would satisfy all the design requirements. Other design details we looked into is the foundation. So typically on a cable-stayed bridge, we have the deck spanning on either side of the panel, but this is not the case here. So we would require the foundation to carry the compression force coming from the deck. But instead of having a large foundation, we decided to design a concrete beam strut. So this is a cross-section view. The beam strut will be running underground, spanning between the foundation of the pylon and the foundation of the hydraulic jet. And this is an elevation view showing the bearing pan, which is the rotation mechanism of the bridge. And this is the beam strut, the concrete beam strut, which will be spanning in between the 2 foundations, ultimately carrying the force into the ground. Another detailed connection, which was a great challenge, was the midspan connection. So our goal over here was to ensure the users to be comfortable using the bridge, and not to have any change in elevation at that point due to different building scenarios. So what we see here is a top view, and we see 4 W sections that are cantilevered and are tapered off to allow for the rotation mechanism to take place without any interference. So if we look at a cross-section view, we have 4 W sections that are laterally braced using cross bracing, with the outer edge locked into a C-section that is controlled by a hydraulic jack. So once we need to open the bridge, the hydraulic jack is activated to allow for the I-beam to move out of the C-section and let the rotation take place. Other design details we looked into are the connection between the cables to the box girder. So over here we see that the cables are connected to the outer side of the box girder, not to have any interference between the railings and the cables to the box girder. And we also see the pontoon connected to the box girder and spanning the full width of the deck. This is an elevation view showing the railings and the cables connected to the box girder and the full length of the pontoon, and we came up with a total of 50 feet requirement for the design of this bridge. And now I'll hand it over to Trevor for the construction sequence.
Thank you, Donna. So I'm just going to quickly go through our proposed our construction sequence. So we start off with the site. We have the Charles River, North Point Park, and because our bridge is symmetrical, we'll just focus on one side. So after clearing the site, we're going to place the foundations. They're in three major components. We have the backspan foundation, which is where the hydraulic jack and the backspan cable are anchored. Then we have the main bridge abutment, which is where the deck and the two pylons are mounted. And then we have the compression strut between the two that Donna spoke about earlier. We move on to the next stage of construction, where we're going to erect the pylons and install a backspan cable with the hydraulic jack. So we start off by prefabricating the pylons off-site along with the gusset plate for the cables at the top. We ship it to the site on a barge, and then the crane will lift it into place. Once the pylons are erected, we have to attach the backspan cables to the top of the pylon. We're going to use a boom lift to get the workers up there, and then a crane would lift the cables to a height where the workers could maneuver them into place. So you have that here, and then you need to attach the jacks to the backspan foundation, and then jack the cables to that connection. So once that's completed, we can start erecting the main span. And if you can imagine the main span, you can break it up into 4 parts. This is the first section, and the 4th section would be on the other side of the river. So this would happen in the same manner as the pylons. It would be prefabricated and then shipped to the site on a barge, then lifted in place by a crane where the workers could attach it to the abutment and jack the cables into place. Here's just a couple photos of sections arriving by barge. Then the middle span of the section is next, and we only can do one of these one side at a time. In the same fashion as the previous section, they would be shipped to the site prefabricated with the pontoons attached to them, lifted in place by a crane. And the deck is over-designed, so it can span between the pontoon and the previous section of the deck, so there will be a temporary connection there. The crane could then move out of the way where workers could then finish the connection and attach the cables. Once this is completed, it can be that section can be rotated into the open position, and we have to do this because there's that connection in the midspan that Donna spoke about earlier, and they can't be erected at the same time or they interfere. So once we move this section to the open position, we can do the same procedure on the other side. This will lengthen the construction sequence a little bit, but it will allow the river to be open to boat traffic throughout the construction process. And Heng will tell you a little bit more about the construction schedule.
Okay, thanks, Trevor. I will talk about the construction schedule. The total time of construction process we estimated will be 1 year. And we split the construction sequence into 6 steps. You can see here. The first step is preparation for the construction. We estimated that this period will last for about 1 month, including prefabricated components, construction equipment, necessary technical workers, rules and regulations for constructions. Next, construction of foundation. Since this step involves a lot of earthwork and concrete work, so this period will take a lot of time. We estimated this period will last for 3 months. After that, erection of pylons. Since we have already fabricated the 2 pylons in the factory, this time will last too long. It only takes half a month. After that, tension of backspan cables. This step only including attaching the cable to the pylon and the backspan